Alright, let us define a context-free grammar formally. Any context-free grammar can be represented by a four-tuple v, sigma, r, and s, where v is a finite set called variables. For the example we saw earlier, v would be a set with variables a and b. Sigma is also a finite set which does not have any intersection with elements in the set v. Formally, the elements in sigma are called terminals. Sigma can also be seen as the alphabet for the language generated by the context-free grammar. R is a finite set of rules. And finally, every CFG should have a start variable, just the way every finite automaton has a start state. S, which belongs to V, is the start variable for the CFG. As programmers, all of you are aware of the significance of balanced parentheses. The language of balanced parentheses is a non-regular language. It can be proved classically using pumping lemma with the 0 to the power n, 1 to the power n example, which you came across several times already, where 0 represents opening parenthesis and 1 represents closing parenthesis. You can clearly show that there's a pump that exists for opening parenthesis. Alright, turns out the language of balanced parentheses can be generated by a context-free grammar. Here is the for tuple that can generate all the strings from balanced parentheses language. Here are the parse trees for these two strings. You can pause the video and try to see if the parse trees make sense. Okay, let me show you another non-regular language that can be generated by context-free grammar, the language of palindromes. The language of palindromes can be generated by this context-free grammar. If you observe closely, the production rules capture the base cases for a palindrome and then have these two recursive rules that generate any palindrome in existence that is made of zeros and ones. To come up with CFG, you have to thoroughly understand the language that you're trying to generate.